Hey, how's it going? So I've got another molecule up today. This molecule is a fairly important molecule actually to treat glaucoma in the eye. So it actually lowers interocular pressure. This is actually a molecule of latanoprost. And obviously from the name, prost indicates that it's part of the prostaglandin class of compounds. What other drugs are part of the prostaglandin class? Those are the nonsteroidal anti-inflammatory drugs. That's one of the most commonly prescribed classes, such as aspirin and ibuprofen, acetaminophen. Those are all members of the same class. As such, there could be potential drug interactions if you're taking latanoprost with a nonsteroidal anti-inflammatory drug, interestingly enough. So, yeah, this is actually, latanoprost is one of the 67, it's the 67th most prescribed drug out of the top 100 in the United States as of 2022. So that's kind of interesting. I guess a lot of people are treating potential complications of glaucoma or just high intraocular pressure. And so let's just kind of look at some of the structures here. Over here on the right, we have a phenyl ring. So that's basically a benzene ring. We just call that a phenyl group. Here we have a hydroxyl group. So again, OH. What else do we have in here? We have two more hydroxyls on this central five-membered pentane, cyclopentane ring. There's also an alkane over here. And then we have an ester group up here. So there's our ester. And then we just have, essentially on the tip of the ester is an isopropyl group over here as well. Now, one of the interesting things about drug discovery, so one of the things if we're studying these drugs is to make a molecular surface. And so I'm just going to make a molecular surface real quick. Whoops. I don't want to spell that right, but it really doesn't matter. And so, I need to select all the atoms when I do that. And then I'm going to select my selected atoms and selected atoms again, right? And let's make my window a little bigger. We're going to make an electrostatic map. Now, a molecular surface is a map of the essentially the van der Waals surface of the drug, but it's a lot more smooth than a traditional space filling model. So you can see a little bit more, and this is what represents what the drug actually looks like when you kind of look at it, if you were to see it in a microscope. You can, of course, the colors are arbitrary, but you can color it by lipophilicity and electrostatics. And so an electrostatic map would have the red regions with different regions of polarity, and that would be negative, and the blue regions would be positive polarity, right? So let's make a map. And here's my electrostatic map. Now, the map, of course, this has a lot of white, which is non-polar regions. And so that's actually important, because if this drug needs to be absorbed in the body, it probably needs to be more lipophilic. And so you're going to look at what's called the log P, or the octanol water partition coefficient. And the higher the log P, the more lipophilic a drug is, right? So, but we do see a couple polar regions, and these polar regions are very important for forming hydrogen bonding and ionic interactions with different parts of the drug surface, right? So this red region is negatively charged. That's essentially, that's electron density. So this is the phenyl ring up here. Now we can't really see the ring, but if we drag here, we can make this surface slightly translucent, right? And then we can see a little bit on the inside of the drug. So that phenyl ring is fairly, that's electron rich. So that has, again, a partial negative charge. So that can actually serve, believe it or not, it looks like it's hydrophobic, but that phenyl ring could actually serve as the hydrogen bond acceptor. And there's a lot of literature that suggests phenyl rings can serve as the hydrogen bond acceptor. Then we have some, the blue regions are partial positive charges. So like here's an OH on here. The other OH is on the other side. Of course, the OH, the oxygen, has the negative charge, and then the OH has the positive charge, right? And then, so the ester, of course, has no hydrogen bond donors, but we do have the red, which is your hydrogen bond acceptor, and a partial negative charge. So we can look at this. Now, one other thing a drug researcher is going to look at when designing a drug is what's called Lipinski's Rules of 5. So what is Lipinski's Rules of 5? We can actually visualize that under ligand properties over here. And if we look at the ligand properties, well, first of all, the number one rule of Lipinski's Rules of 5, and when we say rules, we use rules very loosely because we can't violate them. They're more like guidelines. But for a general rule, Lipinski's Rules of 5 means we want a molecular weight of 500 grams per mole or less. Latanoprost is 432.6, so it's an ideal druggable compound. We want a log P of less than 5 or less. So this log P is 3.84. We've calculated the log P. I think the actual log P is a little bit greater. It's about 4.2 or so, maybe 4.1. But this is a calculated log P, not experimentally determined. So we're actually kind of in the ballpark there. The other aspects of Lipinski's Rules of 5 is we want 5 or fewer hydrogen bond donors. We have 3 here, and those hydrogen bond donors are the OH groups with the hydrogen bonds on there. We have 3 of those. And then hydrogen bond acceptors, you want 10 or fewer hydrogen bond acceptors. We have 4. And let's just see. The hydrogen bond acceptors are basically the oxygens here, the other end of the oxygen. And it looks like MOE is not counting the phenyl ring as a hydrogen bond acceptor. So really we have 5 hydrogen bond acceptors. The phenyl ring, the oxygen on this end of the OH, 2, 3, and then 4 and 5. That makes 5. So really MOE's not exactly, it's not counting the phenyl ring, right? But Lipinski's Rules of 5, this is a really good idea. So if you have a compound, you can quickly calculate Lipinski's Rules of 5. Say, oh, this is probably a good druggable compound. And so latanoprost turned out to be a very good drug. It's well prescribed, it's very useful, and it lowers your interocular pressure. And so that is the molecule. Now, one other thing we want to look at. What's important is lipophilicity. And so let's just kind of take a look at that. I want my surfaces and maps again. And we're going to change this to lipophilicity. Let's see how lipophilic. So lipophilic is more in green, hydrophilic is in purple. And we can just change those colors. Look how green this is. Oh my God, this is very green. There's a little bit of very light purple around some of the hydroxyls, but not much. This compound is very hydrophobic, and it's important because lipophilicity determines what's called the bioavailability of a drug. And that means that it's able to get absorbed into the system. It increases its oral absorptivity. Of course, latanoprost is not orally absorbed because the target is the eye. Well, the eye happens to be right above your mouth. And so instead of taking a pill, this is commonly given as eye drops. It still needs to be fairly lipophilic to cross the membranes that form a barrier to be able to get into the cell so it can do its job. So we have a fairly lipophilic drug, We see lots of green, and this molecule has a very high oral or a high bioavailability. In this case, it would be an optical or an ocular bioavailability because it's given as a common eye drop. I think it's given at night. It takes place. I think its onset of action would be about 4 hours, and it would last all day. So if you're taking this drug, you would typically take this at night, and it would give you lasting effects most of the day. So that's Latanoprost, and that's some molecular surface information. Hope you enjoyed this video here. So if you like that, go ahead and click the like button down below. And feel free to leave a comment if you have a comment. If there's a particular drug or compound you're very interested in, you'd like to see that, go ahead and leave that in the comments below. And go ahead and subscribe to the channel if you'd like to see more and you'd like to learn more. So thank you for watching.